In this video, we're going to continue solving trig equations. What we're going to do is look at a couple different situations. The first one of which is what happens if we have to solve an equation that doesn't include values from the unit circle. And the second thing we'll look at are equations where the period changes. And so let's look at the first solution, or first equation here. 3 times the sine of x minus 2 equals 0. So I think, remember, isolate. We want to isolate our trig function before we do anything else. And so if we do that, we end up with sine of x equals 2/3. And here's a situation where the 2/3 is not one of our values from our unit circle. It's on the unit circle, but it's not one of the special values. And so how do we go and deal with this? Well, we can find, that's where our inverse trig functions come in. We haven't really used them yet. We've used the concept of inverse trig functions, but when we're finding all solutions, we have to go beyond just the value we get from our inverse trig function. And so that's what we're going to do here is use our inverse trig function on 2/3 to find out what angle gets us there, and we want to work in radians, and so when we do this, we find that x is equal to 0.7297. And so that is in radians, and that's the angle measure that gets us to 2/3 as a y-coordinate. Now we know that there's going to be another value on our unit circle, and so how do we find that one? It was easy when we're using our unit circle and have it in front of us, but now we don't have that ability, so how do we figure this out? And so we got to kind of go back to the very beginning of what we learned about trig. And so what we're going to do here is remember reference angles. And so right now 0.7297 puts us about here. Because remember, pi over 2, this is pi over 2, which is about 1.57. All right, and so here is what x is right here. And so we have to think about where else is sine positive. Well, sine is positive in the first two quadrants. And so we know that this point right here also has the same y-coordinate, and it has the same reference angle. Right, so this angle right here would also be x. But what we have to remember here is what we're really interested in finding is what is this angle right here. And easy way to find that is it's going to be pi. Remember, this is pi right here, minus our reference angle, 0.7297. And when we do that subtraction, we get 2.4119. And so there's our two values, our two solutions from 0 to 2 pi. And then to deal with all infinite solutions, because we are asked to find all solutions, we add in our 2 pi n. Let's take a look at this one now. And I think we're doing a pretty good job of modeling our algebra, but I still get people coming up and they don't recognize this as being factorable. All right, and so if you don't recognize something as being factorable, sometimes it's easier to think of this as, instead of trig functions, think of tangent of x being a variable, for example, variable a. And so you'd have a squared minus a minus 2 equals 0. And if we factor that, I think people can look at that and find ways to factor it easier, which would be a minus 2 times a plus 1. And what does the a take the place of here? Tangent x. And so what we would end up with is tangent of x minus 2 times the tangent of x plus 1 equals 0. And now by our zero factor theorem, we have tangent of x minus 2 equals 0, or tangent of x plus 1 equals 0. Now I'm going to go and deal with this one first because that gives me a value on my unit circle where the tangent of x equals -1. And where that occurs is, you know, and I guess it's the fourth quadrant, you could call it -π/4 or 7π/4. It doesn't really matter. I think I am in the habit of going with the -π/4. And then remember it's a tangent function, so we don't have to find the second point. All we have to do is add πn because it repeats every pi. And so there's 1/2 of our solution. Now when we come over here on the left and solve, we get tangent of x equals 2. And remember, tangent has this unlimited range of all real numbers. And so there is a value of x that gives me 2. And so what is it? Well, that's where I'm going to have to go in and figure out that x is equal to the inverse tangent of 2. So I got to use my inverse tangent function. And really, if we're talking exact answers, this would be our exact answer right here. And then all we'd have to do to that exact answer is add πn, add or subtract πn. I think for the nature of this class, unless specifically asked, let's go and find out what the inverse tangent of 2 is, which is 1.1071 plus or minus πn. And so there is my solution to that equation. All right, now we're going to change gears and take a look at this. And what we see inside here is an inside multiplication of 3x, or 3 times x. And we've done this. I think we need to dust our brains off a little bit. The blue curve here would be just what a sine of x looks like. And this value right here would be 2 pi. There's one complete cycle. But now when we do an inside multiplication, remember that's a horizontal shrink of 3. And so what we're going to end up with there are 3 sine curves from 0 to 2 pi. So in other words, you know, and we might remember that our new period, NP, is equal to 2 pi divided by this b value of 3. And so our new period is 2 pi over 3. And so in terms of solving, you know, when you look at this, solving this equation, what we end up with is, well, once again, we want to go in and isolate the trig function. So we'll get this down to the sine of 3x equals 1/2. And so here's 1/2 on our graph. And what we find is that there's 3 times as many solutions in that interval because we have 3 full cycles. Now, it's actually very easy to go and find those solutions. We just continue on doing what we've done previous to this, and just think of this 3x as being a single angle. All right, and so what we want to do is use our unit circle and find out where in the heck is sine, or where the heck is sine equal to 1/2. And we know that sine is 1/2 at pi over 6 and 5 pi over 6. And remember now, we have to add in the plus or minus 2 pi n. And so that there would be the solution if the sine of x equaled 1/2. But we had the sine of 3x, and so what we do is, essentially we took the inverse sine at this point, and so what we're left with over on the left is 3x. So 3x equals pi over 6, 5 pi over 6 plus or minus 2 pi n. And like any algebra equation, the next step is to divide by 3. In this case, I prefer to think of it as multiplying this whole thing by 1/3. And so 1/3 times 3 is our x, so now we solve for x. And now we multiply every part of this by 1/3. and we get pi over 18, 5 pi over 18, plus or minus 2 pi over 3n. And if you look, there's our new period that corresponds to what we found up here. And the pi over 18 and 5 pi over 18 are the first two solutions on our curve. And we can generate the rest of these by continually adding 2 pi over 3 to those answers. Now, one of the things we might be concerned with, this particular one asks you to find all solutions. Sometimes they say find solutions, and they'll give you this, 0 to 2 pi. So find all the solutions on that interval. Well, we know we're going to have 6 of them. Well, 2 of them are pi over 18, 5 pi over 18. And now to find the rest, we just add in our period. And 2 pi over 3 becomes 12 pi over 18. And so my next two solutions in line are going to be 13 pi over 18, pi over 18 plus 12 pi over 18. 5 pi over 18 plus 12 pi over 18 gives me 17 pi over 18. And then the last two solutions here are going to be 25, whoops, excuse me. Let's erase that. That should be 25 pi over 18. And this right here should be 29 pi over 18. And so you got to kind of be careful of how the question's asked. I think most of the time we're asked to find all solutions, but occasionally we might be concerned with a specific interval. And so it just becomes fraction arithmetic, and don't forget your pi's. Okay, we're going to also take a look at how to use our graphing calculator here. First thing, make sure you're in radian mode when you're dealing with these. And then from there, what I tend to do when I see this is I'm going to treat each side of this equation as its own function. So this right here I would enter into my calculator as y1. This is going to be y2, and then I'm just going to find the intersections of these two. And so what we find graphically, if you do this on your calculator, what you should get is sine wave. Ooh, that's not a very good sine wave. And then from there, what we should have is the line y equals x. Oh, is that a bad line? But anyhow, just trying to show the points and over-exaggerate the points. And so what we should find here are 3 solutions. And so then we can use our intersect function to calculate them. And what we should find here is that, now realize we're saying find the solutions. And so our equation only has values of x in it. And so our solutions are going to be the x coordinates of these points. Well, the first one here in the middle is easy. That's 0. And if we know a little bit about the symmetry of these functions, these points correspond to each other. They're going to be rotation images of each other. So if I find one, I know what the other is, and we should find them to be positive and negative 0.9477.